All right, we're going to work our way through the AP Physics C E&M 2017 FRQ number 2. This is an excellent RC circuit problem, so we're just going to work through it as an example. You can find these publicly on, if you like Google released Physics C FRQs, you'll find the College Board site with all of these. There's also a lot of stuff there like chief reader notes and sample responses, like how they'd be scored. They're pretty cool. Anyway, okay, so here we go. We've got this circuit. It says in the circuit above, an ideal battery of voltage V0 is connected to a capacitor with capacitance C0 and resistors with resistance 1 and 2, R1 and R2, where resistance 1 is greater than resistance 2. The switch is open and the capacitor is initially uncharged. Okay, so the switch is open. Okay, at time equals t equals 0, at time t equals 0, we're going to sketch, or we're going to close the switch. Okay, so switch is going to close. As soon as it closed, I want you to look at the circuit that we've got. We will have a circuit where we have two parallel branches. So we'll have like this and this will be parallel to each other. Okay, keep that in mind. Oh, I turned off the stroke eraser. Okay, so we're going to close the switch. It says, on the axis below, sketch the charge Q on the capacitor as a function of time t. Explicitly label any intercepts, asymptotes, maxima, minima with numerical values or algebraic expressions as appropriate. Okay, so if you look at when we close that switch, current will start to flow so we're gonna have a circuit like that, but we're also gonna have independently a parallel branch through R2. Okay, now we are trying to do the charge on the plates of the capacitor as a function of time. This was initially uncharged, and since I have that green circuit, it's gonna charge. Okay, so we're looking at doing a time function for charge on the plate as a function of time. I know it starts at 0, so we're gonna start at 0. There we go, starting at 0. And I know for charging capacitor, like the format is the that growth form. In fact, I already know what it is. We found it before. I'm just gonna write it down. You would not need to know this by heart to solve this problem. You just need to know the shape. So I'm writing it because we're doing a practice here. But this would be the shape. 1 minus decay becomes growth. RC. There we go. Like, that's the shape. That's, oops, I didn't mean to do that. That's this kind of shape where you've got an asymptote at QF. Like the final value that you're going to get to, or you're going to approach, is QF. Let's see if I can make an asymptote. All right, that's good enough. Yeah. But it says we are supposed to label any intercepts and asymptotes. So I might even just really say asymptote. Yeah. I need to label the value that asymptote is at. Okay. Now I know what it is. It's QF. Okay. And I'm going to erase this to get it out of the way. Okay. I know it's QF. Okay. But I'm supposed to use with numerical values or algebraic expressions. QF is not something they gave me. Okay. If I look around at the things they gave me, there is definitely no QF. I have to find a way to express QF in terms of things that they did give me. But they did give me some stuff. For example, I know the capacitance of the capacitor is C0. Okay, I know that. And I know in general, like capacitance is charge over delta V. Okay, so I should be able to do this. I should be able to say, well, the capacitance C0 is equal to, at the end, when it's fully charged, final charge on the plates divided by final potential difference across the plates. So I just have to figure out what the final potential difference is across the plates, and that will get me what QF is. So, because QF is going to be C naught times the final potential across the plates. So if I look at the picture again, I want you to think about a really long time after this has been allowed to charge. At some point, the charge is going to build up, build up, build up, build up, build up on this thing. I'm going to get rid of some of this stuff. The charge is going to build up and build up and build up until current stops flowing, and I guess I'm going to put that back around this particular branch of the circuit. And when that happens, when the current stops flowing, it's because the potential difference across the plates is the same as the potential difference provided by the battery. Okay. Only at that moment will the current actually stop flowing, and we will stop charging the plates, and we have hit maximum charge on the plates. Okay. So maximum potential difference across the plates, like delta V final, will be the battery. So V naught. Okay. So, sorry, I'm just going to keep drawing and erasing and drawing and erasing and drawing and erasing. So when I come down here, that is going to be V naught, which means my final charge on the plates will be C naught V naught. And that's what needs to, I need to label my asymptote. Okay, so I do need to label that value because they said any intercepts are asymptotes, any maximums or minimums. I guess the intercept here is 0, 0,0. You don't need to label 0, 0. That's pretty obviously at 0, 0. Okay, but that asymptote I needed to definitely label. Okay, if you're curious about the grading of this particular problem, this graph all by itself has 3 points. It says for a concave down curve starting at the origin, that's a point. For a horizontal asymptote, that's a point. For a properly labeled horizontal asymptote, so that label, that's a point. Okay. Part B. On the axes below, sketch the current through each resistor as a function of time t. Clearly label the two curves as I1 and I2. Sorry, I have hiccups. The currents through resistors, I1 is through R1 and I2 is through R2. Oi. Explicitly label any intercepts, asymptotes, maximum, minimum, or numerical values or algebraic expressions as appropriate. Okay, we have to get 2 lines on this graph. Okay, and they need to be they need to be very well labeled. Okay, so let's look back up at the picture again. Remember how I said there were those there were those 2 currents. So there's this essentially is okay, sorry. Let's do this. Okay. This is I1 and this is I2. Alrighty. I1, that current is the current that is charging the capacitor. It's on the branch with the capacitor. So that current is not going to be constant. That will be a current that starts off strong but decays. Okay. Nope. You don't need to see that. Okay. So I1 is going to follow the time function for a charging capacitor, which I'm just going to write over to the side and I'll get rid of later. But I1 as a function of time should be an initial current through resistor 1 times decay, like this. Okay. Where in this case, the the R right there is only the R that is involved in the circuit with the capacitor. So just R1. Okay. But that's actually not necessary. I'm just trying to show you the shape. I know that whatever this is going to start off strong and decay towards 0. That's the shape I know that it's going to make. So that's the shape. Okay. So maybe here, let's just say it starts here. This is the initial current through I1, and I know it's going to make an asymptote down to 0. Okay, so maybe like that. That's current I1. I do need to know where it starts. Okay, so I need to know what my initial current is through here. And initial current is the current that we had at time 0, and that's when the capacitor was uncharged. So if you remember back to our words that we talked about on the last video, That would be immediately after that switch was closed. And we said if you had an uncharged capacitor immediately after a switch was closed, you can treat that as a wire, essentially, which means I1 is just the current you get from, it has a potential difference of V naught, okay? And it has a resistance R1, so I1 would just be V naught over R1 from an Ohm's law, okay? So, oops, yeah. This is going to be V naught over R1 as the intercept. That's supposed to be a divide. Let me try and do better. V naught over R1. Okay. Okay. But we still have to do I2. I2 is the current through the other resistor, but this one has nothing to do with the capacitor right now. Okay, this is just a nice, basically just this branch all by itself. It also would have V naught across it because it is parallel with V naught. Okay, and it has resistance R2. So the current is going to be V naught over R2, but it's independent of this middle bit. Like, it's almost like the middle bit isn't even there and you're just going around and around and around. So this current is going to be constant, and it's going to be a constant V naught over R2. So I know I'm going to have to draw like a straight, flat, horizontal line for this. I do need to be careful though that I put it in the right place. They said that R1 was bigger than R2. So that means that V naught over R1, the current through R1, which is V naught over R1, if R1's bigger than R2, this should be less than V naught over R2, which is the current through R2. So V naught over R2, I need to put as an intercept on here, and it's got to be higher. I don't know how much higher because we don't have numbers. And then that just doesn't change, and that's I2, like that. Okay. Yeah. If you're wondering how this one breaks down, this one has 4 points attached to it. Okay. We're already halfway through all of the points for this whole problem, and there's quite a few parts left, but these graphs are definitely like the lion's share of these points. So this one's with 4 points. It says, for showing that I2 is horizontal with the correct vertical intercept. So that's a point. For showing that I1 is concave up and asymptotic to I equals 0. That's a point. For correctly labeling the vertical intercept of the I1 graph. That's a point. For drawing the I2 graph always above the I1 graph. That's a point. Okay. I guess I left room. I should have been done doing my work in this little room that I had down here. Anyway. Okay, moving on. The circuit is constructed using an ideal 1.5 volt battery, an 80 microfarad capacitor, and resistors R1 equals 150 ohms and R2 equals 100 ohms. This switch is closed, allowing the capacitor to fully charge. Then the switch is opened, allowing the capacitor to discharge. Okay, so just really quick, let's look at this picture again. So they closed it and let the capacitor charge up. It charged up to 100% to what it was, so that like the potential difference across it is 1.5 volts, because this is 1.5 volts. They've told us a number now. And then they're going to open it again. Okay, so that was when it was closed. It got charged up. Then they open again. I want you to think about this circuit when this is open. If this capacitor is charged, it's basically going to act like a voltage source, kind of like a battery, but it's not going to stay like that. It won't stay like that. But it starts off like that immediately after the switch is open, because I still have this circuit now, essentially. Once I open that switch, it essentially cuts off all of this. It's just cut off, but it leaves behind this circuit. So the capacitor is going to provide a potential difference across the series of R1 and R2, and we're going to get a current going through both of them, some current, okay? And then as that thing drains, that current's going to fall off, but immediately after the switch is closed or opened, this is what I've got. I got a 1.5 volt difference where the capacitor is, and I've got I going through both R1 and R2 because they are in series. So let's go see what they want us to do. It says, blah, 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 the time it takes to charge the capacitor to 50% of its maximum charge is delta TC for time to charge. The time it takes for the capacitor to discharge to 50% of its maximum charge is delta TD for discharge. Which of the following correctly relates the two time intervals? Okay, so which one takes longer? Charging it or discharging it? Like by half. You could put any number there. They're like, which one takes longer, to fully charge it or to fully discharge it? Or you could do anything. They just chose 50%. I don't know why. They just did. Okay. This is actually where the oft elusive time constant actually becomes useful here, in that when it was charging, okay, the time constant was RC, but when it was charging, go back up to the picture again, okay, when it was charging, the circuit that the capacitor was like on was this circuit. Okay. The only resistance in that circuit was R1. Okay. So the time constant for that is R1 times C naught. Like that's the time constant. Okay. That's the time constant. Remember, the time constant tells you basically how long it takes this thing to charge. Technically, the time constant T or tau is the time it takes to get to 1 over E of the max charge, but it could be also a bellwether for how long it's going to take to go 50%, for example. Okay. Basically, the longer the time constant is, the longer it's going to take this thing to charge or discharge. So let's look at discharging. Okay. This time, the circuit that is involved when it's discharging looks like this. Same capacitance, but now the resistance is, both of the resistors. They are in series with each other, so like the total resistance is the sum of them. Okay, so if I go and find the time constant for that one, that's going to be R1 plus R2 is the resistance part, and then C naught, and that one's just bigger. Okay, so it's going to take longer. Discharging takes longer because the time constant is larger. Okay. So the time interval, what is it? There it is. Okay. The time interval of the time to charge is less than the time to discharge is the one we want to check off, and it's because the time constant is longer for discharging because the resistance is more. Okay. You can just say, like, what I just said in words would be enough for this. If you're worried, if you want to know about the points, there's only 2 points for this. It says, for indicating that the equivalent resistance during discharging is greater than during charging, that's a point. For a statement relating the greater resistance to the greater time constant or to a smaller current, that also works. And then also checking the thing. You have to check the thing and explain those two things. The example they give, it says, because the resistance as the capacitor discharges is greater than when it charges, the time constant is larger for discharging. Therefore, the time to charge 50% of its maximum charge is less than the time to discharge 50% of its maximum charge. Okay. That's their example. Nobody ever actually really talks like that. But, you know, I guess that's their ideal answer. Okay. Keeping going. Here we go. D, part 1. Calculate the current through resistor R2 immediately after the switch is opened. Okay. So this is, the thing's all charged up. This is before it has discharged anything. At that moment, the capacitor would just be acting like a battery of 1.5 volts. Okay, so it's all charged up. We open the switch. So all charged up means this is going to be 1.5 volts because that's how it was done with the battery. We open the switch and basically that becomes the quote battery of this 2 resistor circuit. Okay. So the current through the R2 resistor is the current through the whole thing. And it is 1.5 volts over the total resistance, which is that. Which we have numbers for, so I should put those in too. Shoot, what were they? You know what? I have them over here. I'll just write them down. It was 100 and 150. Okay. You pop that in a calculator and you get 0.006 amps. Okay. Or if you want, that's 6 milliamps. Okay. They have both on the thing. So, well, they're both valid. Okay. All right. Part 2. Oh man, we've already passed 20 minutes. Okay. I'll trying to finish this fast. Is the current through resistor R2 increasing, decreasing, or constant immediately after the switch is opened? Well, immediately after, like right when the switch is opened, we get that much current. But as time goes on, the capacitor is discharging, which means the potential difference across it is going to get smaller, which means the current's going to get smaller. Or you could just say, well, current decays as you discharge a capacitor, so it's going to be decreasing. And this is just 1 point. So 1 point for clicking decreasing and for correct justification. So you could say things like, once it starts discharging, the delta V across the resistor decreases or gets smaller. Sorry, not across resistor. The delta V across the capacitor decreases. Okay. Therefore, the current through, well, the whole thing decreases. I'll just say R1 and R2 decreases. You could say that. You could just talk about as it discharges, current decays. I don't know, like whatever you want. There's actually a lot of things you could say. So something like that. Okay, especially since you just recently found current by doing potential difference across the capacitor divided by total resistance. It's kind of nice to be able to go back and say, well, that's getting smaller, so current would get smaller because I just did this equation. Okay. Okay, E1. Wait. That was D2. Okay, E1. Calculate the energy stored in the capacitor immediately after the switch is opened. So this is when the capacitor was charged to 1.5 volts. So I have the delta V across the capacitor. It's 1.5 volts. I also know the capacitance. They told us, gosh, what was it? What was it? 80 microfarads. Okay. Well, heck, right there, I know an energy stored in a capacitor equation that just has delta V across the capacitor and capacitance of the capacitor, and that's it. It's this one. So just plug your numbers in. That really is it. There's nothing else to do here. 80 microfarads. Delta V is 1.5 volts. Since I've got a micro in there, I end up with 90 microjoules. Okay. You also could just turn the microfarads into farads and you'd get like point 0, wait, how many zeros? Whatever, you get a very small number of joules, or you can leave it as a micro, and the micro just shows up in the answer too. Okay, that's 1 point. There's nothing more to do on that one. Okay, E part 2, calculate the energy dissipated by resistor R1 as the capacitor completely discharges. Okay, this one's interesting because the current decreases over time. They basically want us to add up like all the energy dissipated, but only by resistor number 1. If they had asked us the energy dissipated by R1 and R2 together, it would have been this much. It would have been 90, because that's how much was stored in the capacitor when it was fully charged, and then it's going to fully discharge and give up all that energy to the 2 resistors. But we only want 1. So what we're going to have to do, is find the current through resistor 1. Unfortunately, it's going to be not a constant. And so then we'll have to integrate from like time 0 to time infinity. Woo. Okay. It's not that terrible though. Okay. So like, I already know that this is a thing. Yeah, that's a thing. I already know that. So let's use that. I know that that's the current through through R1. In this case, I naught is, well, it's what we found. Okay. What was it? It was 6 amps. Yeah. This is the current through I1 and R2. So we said through R2, but it's also through I1. So my initial current is that. So what is that? 0.0. I'm going to do this in amps though. I'm about to do an integral. I don't want to mess with funny units. Oh, there we go. Okay. So there's my total, my initial current. And then I got my E to the negative T. Okay. The RC needs to be the R in this whole circuit, which is R1 plus R2. Oh, stop it. Sorry. Go. Okay. All right. Okay. I'll do this off to the side. Okay. And then I'm going to call this one tau. Stop selecting things. Okay. So, oh shoot, was this 100 and 150? Yeah, it was. Okay, so tau is 250 ohms times 80 microfarads. So, okay, that means I80 times 10 to the negative 6th. Okay. So tau is, oh, hang on. I have to pop that in a calculator. It's after 9. I'm old. I can't do things after 9. Okay. Negative 6th. Oops, I did negative 9. Okay, 0.02. That's what that is. Okay, so that goes here. Okay, so I've got a function. Okay. Energy dissipated will be in general, power is dE dt. Yes. So dE equals P dt, which means if I integrate both sides, bloop, bloop, okay, I should get the energy dissipated will be the integral from 0 to infinity to let it fully discharge of power. Now I've got current here, and I also know resistance. This is resistor 1. What we're going to do is we're going to do that power is, what is power? It's I squared times R. Okay, that's where we took the original power equation and replaced delta V with I times R, because delta V equals I times R according to Ohm's law. So down here in my equation, I'm going to do I squared R, where it's R1, because that's the resistor that I'm concerned with. dt. And then I is this function that we have up here, which is 0.006 e to the negative t over 0.02. So if I do all of this, if I stick that in there, let's see, I'm just going to draw an arrow. Take all of this and plug it in there. Okay. That is going to make my integral look like from 0 to infinity. Oh, let's see, squaring a function. So that just makes the exponent be squared, right? Yeah. Well, okay, I'm going to do this first. I'm going to write it out squared. What was it? 0.0006? Shoot. No, 2 zeros. Okay. 0.006 e to the negative t over 0.02. We're going to square that. We're going to multiply by R1. R1 was 150 ohms. And then I have a dt. Okay. Well, I've got some nice constants that I can pull out to the front. Let's do that. Okay, so I've got a 0.006 squared that I can pull out to the front. So that's 0.00036? Shoot. Is that right? 0.006 squared. Oh, wait. Nope, there's another 0. I missed a 0. It's a whole nother 0. Gosh, is that really right? Because you do 36 and then you add the 2. Yeah, that is right. Oh, and I forgot the 3. Sorry, it's 36. There we go. So that, and then I've got the 150. I can pull that out to the front so that I'm integrating from 0 to infinity of, so I've got e to the negative t over 0.02, and that's squared. So don't get me wrong, that's just, I can just move the exponent, like I multiply the exponent by 2, right? I think so. Let me just check on something. Boy. Yeah. Okay. So what I'm left with is e to the negative t, and then, oh, sorry, negative 2t over 0.02 dt. That's all that's in the integral. I can clean this up a little bit in that negative 2 over 0.02 is 100. It's kind of nice. I can also clean up the front. This monstrosity times 150 is, I went and did calculator while I had it paused, 0.0054. Okay. And then integrate from 0 to infinity of this thing comes out to negative 100t is what it comes down to. Okay. And then dt. And now I just need to integrate that and evaluate it. So, almost done. Okay. Oh, integral of a e function. You still get the e function. It still exists. And then you divide by the exponent, I think. Yep. And then evaluate it from 0 to infinity. Okay. And then if we do that, we get the constant. And then we have, well, I'm going to bring up that negative 100. I'll just do this. Okay. And then I've got e to the negative 100 times infinity minus e to the negative 100 times 0. Lovely. Okay. And if I remember my e rules, okay, I had to look that up to make sure because I was like, what? E to the negative infinity is in fact 0, and then this is e to the 0, which is 1. That one I actually remembered. Okay. So what I've got here is Okay, I've got a negative, well, 0.00, I divided by 100, so 0.0054, woof. And then I've got 0 minus 1. So I end up with this number times negative 1. They're both negative, which means I end up with a positive answer of this many joules, or if you prefer, 1, 2, 3, 4, 5, 6, yep, 54 microjoules will also work. Okay, I think there's another way to do this too, but I don't understand it. This is the way I would have done it. And this video has gotten very long. 35 minutes. That's almost all the time you'd have to do one FRQ on the test instead of, this is only one of 3. Anyway, that is the last problem on this problem.